and for today's presentation we will look at domain adaptation for deployment-ready models. So domain adaptation is actually the problem that occurs after you do the monitoring. So Yuri explained why monitoring is very much needed when you are in deployment models. The biggest problem you would face is domain adaptation, and today we will see how will you be able to detect it and how will you be able to remedy this problem. So usually for machine learning projects in class while you're studying, so first step is to gather your data, do some data pre-processing, build your model, do some inferencing, and then some reporting. See, this is a very straightforward process. See, the problem in this graph is just it goes straight forward, so it's only going forward. I would say that it should be going like this. So once you did the data visualization and you did some inference, you will see that there are some problems in your model that need to be fixed. So the three basic assumptions that you can make, where are these problems coming from? So first thing is maybe some changes in your business realities. So if you are for example, a Kazan Express or AliExpress company, and you added new products or something like that. So if there are some changes in your business, whether you are getting bad data, for example, your sensors, some of the sensors have been affected by the weather or something like that, or your models, they just need improvement. So they haven't been trained in a long time, so they just need a little bit of improvement. Where should you go to check these problems first? So the first place to go to is your data. So you must check your data. Verify if there are some outliers. Check for some missing features that can arise from problems in the sensors. And check for distribution shifts and coverage. So what we will be talking about mainly is these two. So for missing features, it's probably a hardware problem or some software update that was wrong, so it's not a very big problem for machine learning. But distribution shifts and coverage, this is the type of problem that you must be working with. Coverage, again, it's an easy problem. So for example, you are a company like Yandex Taxi or Uber. And when you did the training, most of your training data was in the morning period or at lunch, for example, just supposing. But once you deployed the model, you found out that a lot of your clients are taking taxis at night. And you don't have enough data at night for the training. So this is what we're saying, what we're talking about when we say coverage. So your training data did not really cover the whole search space or the whole input space of the model. Now, for distribution shifts, this is a different problem. So distribution shifts can arise, as Yuri has explained. Maybe your data was following a certain distribution, but the distribution changed in deployment. This is easy to look at when you have numbers. So you can just build a distribution. But we do realize that data does not just come in numbers. Data can come in, like there is text, there is images, there are videos, audio, and different types. How will you be able to detect this distribution shift? So it does exist, but we don't have enough mathematical foundation to validate the existence of such distribution shifts. For images, it's easy because you can just look at the images and see that these types of images are different. Some projects have been published by Google, so it's called the PAIR projects, People and AI project, something like that, where you can get better insight and understand your data better to see these distribution shifts. But again, it's still very naive. It's still very in the beginning. What we can do is, as we said, so there you go. So this is one of the ways you can do this. So this is called, is part of the project PAIR from Google. And it's integrated now in TensorFlow Extended. So TensorFlow Extended is nothing but TensorFlow, but surrounded with other types of code. And this type of code will give you these features. So you can find comparisons between different days, between training and deployment. So you can make these comparisons and verify whether there is a problem or not. So if there's no problem, good luck, you have a great model. But if there is a problem, it's basically going to be something called domain adaptation. Now let's look at this problem. So this is source domain. This is your training data. You built a normal linear classifier. So it's a very simple case. As you can see, this is class 0, class 1. Now when you introduce the new deployment data, sadly, it was not following the same distribution and it came in here. So this classification line or classification boundary definitely will misclassify these. Now in this case it's very easy because it's a linear boundary and the data is pretty well separated. Now if you go to a neural network where the decision boundary is quite nonlinear and usually your classes are not this separated, meaning this misclassification will not be as simple or as small. Now what we want is this one. So a cross-domain classifier, we want to build something that is able to work for both old and new data. Now let's put this word that I just described, which is able to work for both target and source data, into research terminology. So the first goal that we want to achieve is something called domain invariance. Domain invariance means your model should perform similarly on both domains, regardless of what domain it is. So for domain adaptation, there are two domains. There's also domain generalization, where you may have lots of other domains. So domain invariance is a property that is required in your model. It should perform similar or in the same manner through all different domains. Why am I saying this? Why should it perform in the same way? So for example, I think you've heard of the problem with iPhone's facial recognition software, where it was not able to work that well on Chinese people. So if the owner of the cell phone is Chinese, any other Chinese person can just come in and access it. That's a problem, but it's not a big problem if you look at it, because the consumers of iPhone are not mainly Chinese people. So for example, the accuracy of the facial recognition software was probably 99%, so it was great. But on this category, it was horrible. And this error, even though it is very small, maybe even you cannot detect it because the accuracy and all other metrics were very nice, but there was a small error which was racism. So this is what we're talking about, domain invariance. So you are able to work on all domains equally. And this is very, very much needed because you don't want to fall in the problem of having a bad reputation. Now, category informative, this is very, very easy to understand. So any CNN network, any neural network must obtain information that is useful for classification. So again, what we want is we want an encoder. Who's familiar with what's an encoder? So encoder, decoder? Nice. So we want the encoder to generate features that are domain invariant and category informative. Now, what is an encoder again? Let's play with this terminology a little bit. Now, a neural network, when I say the term neural network, I will only be speaking about classification neural network, which is a normal feed-forward neural network. So there are no convolutions, no anything else. Now, what I want is, so my classifier will definitely be this feed-forward neural network. So whether you have a CNN, whether you have any other model, the ending is always going to be a normal feed-forward neural network, in most cases. What I want is my encoder, which could be a CNN, could be a normal feed-forward neural network, could be a recurrent neural network, no problem. As long as it gives me this type of latent representation, domain invariant, and category informative. Where can you put this line of, this is the encoder, this is the classifier? Anywhere you want. Yeah, you can play with this to get better results. So we will see a trick that you can add on this layer where you will separate encoder and classifier. And this separation, you can play with it however you want to improve the accuracy or to make your model less complicated. So let's just look again. So as you can see, this is MNIST. I hope it's visible. This is MNIST. And this is another data set called SVHN. So MNIST is very famous. It's handwritten digits. You're familiar with MNIST, right? Yes. So it's for handwritten digits. Now, SVHN is for street view like numbers. So it's more, there are numbers, these are numbers that are made using a computer. So it should be easier to classify, right? Now, if you train a model on MNIST and test it on SVHN, given that there are 10 classes, you will get an accuracy of 8%. You see, 8% is even worse than a random classifier. So your model is worse than random. And that's the problem that you can get with domain adaptation. Now, if you do the opposite, train on SVHN and test it on MNIST, your model is, again, not that bad. So it's 60%. But still, it's a huge decrease from 99% to 60%. And this is the problem that we're trying to help. So the goal, again, here, you see, we want the latent representation of the numbers not to be splitted as in here, where this is SVHN and this is the cluster of MNIST. We want it to be split like this. We want it to be split regarding the class and not the domain. So the domain did not really influence where the picture is set. So this is the goal. One of the most famous papers in this field, it's called Duplex Scan. So Duplex Scan uses, of course, generative adversarial neural networks. And you see this word duplex because it has it has two discriminators. Who's familiar with what's a generative adversarial network? Nice. So what it does is just it generates pictures. That's it. So you get, yeah, it's very simple. It generates pictures and it's very good at this job. So what I want is this. So my model, the thing that I will deploy is only the encoder and this classifier here, right? So all of this, after training, we will just throw it away. We don't need it. So what I need is this encoder to generate a latent space that is domain invariant. You can define the word domain invariant in this term. So we're just going to take this domain invariance and define it in another way. I want a latent representation that can help me generate pictures from all domains. So it's just a different way to look at the term domain invariance, which is able or useful to generate pictures from all domains. So basically, I will input this 5 and try to output something like this. You see? Try to generate an image from the other domain. This will help me build a model that when it looks at this 5, it does not really understand whether it's MNIST or SVHN. It will generate 2 different 5s for both domains. And this is domain invariance. So Duplex Scan, how do they do that? Simple. As you guys are familiar, I think you already know. So GANs, what they take as input is just some random noise, right? Now we will take this random noise as the latent space of an image. We take a latent space of an image, generate 2 images, 2 other images. 1 from each domain. And then we have this one. A discriminator and another discriminator. Now the discriminator's task is to tell whether this is real or fake, right? So that's what it's going to do. It will sit here. So it's for the source domain, and this is for the target domain. It will sit here and say, this is real data, this is generated data. This is real data, this is generated data. That's what it will be doing. The generator will obviously be trained in an adversarial way to fool the discriminator, making it better at generating images. And that's how you end up with having a better encoder, or an encoder that satisfies both of these features, domain invariance and category informative. If you look here, if you look closely to the paper, you will see that it does not just output real or fake as a normal GAN would. So it's not just real or fake, but it also tries to classify the image that it has generated. So again, the information is not just the category information. It does not just come from the classifier in here, but it also comes from both the discriminators. It's to force the network to retain this information, okay? Again, I think you've seen this picture with Yuri before. Everything I've just said, where you change the model and build this. So what we started with was just an encoder and a classifier. We saw that it was bad, so we had to change the model or improve on it. So we added all of this, and then we're going to test it again. So there's this cycle that is always repeating. So you're always going to find problems in your model, and you always have to be fixing it. Now, all of what we talk about is ML code, what's in here, but for machine learning models to work, they need a lot of other stuff. So lately, there was, like, I think a year ago, there was a very big company which tweeted out, so we built a great model in just 3 weeks, but it took us more than 12 months to deploy it. Because when you are deploying, so for example, for software requirements or for software engineers, they usually have very rigorous methods or methodologies to build their software. And their software must have some characteristics that it abides to. So it must be scalable, it must be distributed, it should be, so for example, reusability, and all of these things, their software must abide to. But for our case, for machine learning, it's just usually they just give you a data set and hope for the best. After 6 months, you will give them something. So there's no way to predict how much time you will take. There's no way to organize the machine learning process. So what happened is Google tried to fix this problem, and they outputted a lot of their source code that handles these problems, and they're trying to make it's like software engineering for data science. So they're trying to make data science more abiding to these requirements. So what we usually care about is this one. So machine learning basic tasks, we have labeling the data, verifying the quality of the data, so coverage, minimizing dimensions, PCA, TSNE, and other stuff, maximizing accuracy metrics, hyperparameter tuning, model selection. So we have lots of tasks for machine learning. But again, machine learning models are just code. And most code must abide to these requirements. So scalability, reusability, extensibility, monitoring, as Yuri have said, using the best practices, safety, privacy. For example, for best practices, how do you upload an image to your model? How do you make predictions? Where should your model be located in? So many of these questions that should be answered. Now, thank God, Google has open sourced most of its private code to handle these problems. So we have for data ingestion, we have this thing called example gen. It's a class. Statistics gen, schema gen, example validator. We have some transformers. This is the trainers. This is just normal TensorFlow. And I think you're all familiar with normal TensorFlow. So, but the rest is all new. So this is model analysis. So this is for validation and for serving. Now let's go back just one simple slide here. So again, TensorFlow Extended provides you all of these features in very interactive forms. So as you can see in here, everything is very well organized, it's a lot of visualizations, very easy to use. But the problem in this system are these. So they are using lots of libraries which are built on Python 2. Of course, Python 2 will no longer be in use after 2020, but so far you will find a lot of compatibility issues if you're going to just use all of their stack. For example, with Kubeflow, it's going to be a lot of problems. You're going to find lots of library conflicts and the diversity of the data. Sadly, what they outputted is only this, so example gen. Example gen only works with CSV data. So if you have images, if you have videos, audio, it's going to be a very, very difficult task to do it. And if you want to do it manually, they recommend to use Apache Beam. And Apache Beam is not very good when it comes to Python. So they released the new Python 3 version for Apache Beam, but it's full of bugs and it has never been tested. So it's just go and play with it. So again, diversity of data is not going to allow you to use what we just described. And yes, and for data preprocessing, they don't have very good data preprocessing techniques, methods. So they want you to have out of the box, very well distributed data preprocessing, but they only provide it for CSV files. Anything else, you're going to have to do it from scratch. So there are other providers for such infrastructure that work very well for data preprocessing, so you can do the mix. Okay? So this is it. This is the presentation.